Good day, I'm Dr. T and welcome to my office. So today I would like to talk about ways atoms interact with each other and form the stuff around us. There are three major ways of atoms interacting with each other and forming substances. There are two caveats I'd like to make. First is a very minor one. There is some research indicating that there might be a fourth way that molecules can do this. I'm not going to go into it because the research is still ongoing and because the fact that we're just now figuring this out, if it does exist, means that it's not common. Second caveat is that these are going to be kind of three overarching boxes that we're putting chemicals into. Boxes and these concepts of categories are a human invention. Nature does not have them. Nature is not beholden to us to conform to our ideas of what it should do. So there will definitely be cases of substances that do not fit neatly into any one of these boxes. Specifically crossing over between two of these categories because nature is doing nature and we are trying to categorize it, and there's of course typically overlap between our categories. Okay, so the first category of ways atoms can arrange with each other is known as a covalent bond. So in a covalent bond you have two atoms and they're going to take their atomic orbitals, and one atomic orbital from one atom and one atomic orbital from the other atom are going to interact with each other. They're going to form a new, what we call molecular orbital out of those. And in that molecular orbital will be a pair of electrons. They are sharing that pair of electrons. The two positively charged nucleuses are attracted to the electrons that are between them, and thus the two atoms are now bonded to each other. This is what we call a covalent bond. There's a couple of different types of covalent bond that I'm not going to go into detail, at least at this time, about. But needless to say, you now create a discrete relationship between two atoms. Now, if you can create discrete relationships between two atoms, you can, of course, then start creating webs of atoms. And there's a couple of ways this can go. So if I have, say, a group of half a dozen or a dozen or even thousands of atoms, but a finite number of them, I can arrange those atoms so that they have discrete relationship with other members of the group, but fundamentally they form a clump that has covalent bonds between the members of the clump, not necessarily all the members, just, they're connected somehow into that clump, but there are no covalent bonds outside of that clump. This clump is what we call a molecule. So molecular substances will have a fixed number of each type of atom in them, and they will have a fixed arrangement. So if I was to look at water, I would have an oxygen atom in the middle, and then I would have two hydrogens bonded to that oxygen atom, and it kind of looks like Mickey Mouse ears. If I was to have, say, glucose, then I would have 6 carbon atoms. 5 of them, as well as an oxygen atom, form a 6-membered ring by sharing electrons between them. Each carbon atom is also connected to an oxygen, and there are hydrogens galore surrounding that. But this is a single clump of atoms that contains 6 carbons, 12 hydrogens, and 6 oxygens. These are a discrete finite clump. Now, the alternative is, instead of creating these discrete finite clumps, I can create webs of atoms. So if I were to say, look at a diamond, if you zoomed in, you would see a carbon and it would be bound to 4 other carbons, each one bound to 4 other carbons, and the whole thing is just bunches and bunches of carbons. In this case, there's no defined number of carbons. It's just however many there happens to be. This is what we call a covalent network solid. You've got a solid and you got a whole bunch of things creating a giant web. Hence the network part of it. Now, covalent network solids can come in 2 flavors, one of which is when the atoms are arranged very orderly. They have this very repeating mathematical pattern. That pattern is called a lattice, and substances that form with a lattice are called crystals. Alternatively, if I instead of am talking about diamond, which is a crystalline substance, it has a nice lattice, I wish to talk about glass. Glass is a covalent network solid, but it does not have a repeating pattern. There is no strict lattice. It's silicon and oxygens covalently bonded to each other, creating a giant three-dimensional web, but it's not a particularly ordered three-dimensional web. I will point out it is definitely a solid. It's not a liquid. That is a myth. But it is not an ordered web. In that case, that is what we call amorphous. Now, looking back at the crystalline structures, I should point out a couple other ones. Molecular compounds can arrange themselves as molecules into a lattice. They're still a molecular compound. They just happen to be in a lattice. We see that in, say, an ice crystal. The molecules arrange themselves nice and orderly. Additionally, certain substances can form crystalline structures with different lattices, so they can arrange in a somewhat different way depending on the conditions that they experience. These different lattices for the same substance are known as polymorphs. This is a little bit more of an area of importance, as it turns out for molecular species that clump together, the polymorph can actually have a fairly important effect on the properties, especially for things like pharmacology. Certain polymorphs will break apart and dissolve at different rates. And of course, how fast your pill dissolves is kind of a big deal when you're talking about, well, pills. Okay, so that is the covalent. You can have molecules, or what we call a molecular substance, or you can have covalent network solids. Both of those are relying on covalent bonds. The next one I want to talk about is the ionic bond. I use the air quotes because in this case, it's not really a bond. A bond implies shared electrons. And for ionic substances, they don't strictly share electrons. Now, some of them will overlap with covalent substances. So once again, they can be in the borderline on here. Ionic substances are going to be comprised of cations and anions. Cations contain a deficit of electrons, therefore they're positively charged. They can be a single atom, or they can be a molecule that has lost an electron. If it is a molecule, then we no longer call it a molecule, we call it a polyatomic ion. Typically speaking, cations are metals, although there are examples where they are nonmetals for cations. The counterpart is going to be the anion, and these must also be present in an ionic compound. Anions are atoms or molecules that have gained an electron. Once again, molecules that have a non-zero charge are called polyatomic ions. So in this case, we have atoms and molecules with a net negative charge because they have a surplus of electrons. Cations and anions don't have to have a charge of 1. They could be greater than 1. So, +2, +3 for the cations, or -2, -3 for the anions. Now, opposites attract. So you can get your cations to attract your anions, and in a solid, what you're going to do is have a whole bunch of cations and a whole bunch of anions all attract to each other, and they will start ordering themselves in a lattice. So you get a crystal structure. And thus that lattice is going to create this really interesting network of all these positives and negatives attracted to each other. Now, I should point out once again, you can have multiple different types of lattices. Typically, what you see is this kind of alternating 1-to-1 cation to anion ratio in this very regular cubic lattice. Not everything is in a cubic lattice. Not everything is in this 1-to-1 ratio. It's just that's the easy one to draw. And trust me, I've tried to make models of the other types of lattices. They're a pain to make. The cube ones are really easy. Table salt is in that kind of nice alternating, very cubic structure. So that's typically the picture you see. But that is not the only lattice in town. Okay, so that's your ionic compound. Ionic compounds tend to be actually a bit more stable, a bit sturdier, because you have all of those interactions. They'll have much higher melting points. Now, you will see in some classes, specifically biology classes, which will say ionic bonds are weaker, they are more susceptible to being reconfigured, let's say, by water. Water is able to interact with ions in a way that kind of makes a pseudo-lattice. But strictly speaking, that's not breaking the bonds, that's reconfiguring them. If you want to just heat them up and melt them, ionic compounds have very high melting temperatures. Now, that actually leads into the last type, and that is the metallic bond. So metallic bonds, as the name would suggest, are typically made with metals, although some nonmetals can interact with metallic bonds, like the carbon in steel, although, once again, that's kind of stretching things. Because, once again, nature doesn't necessarily fit our boxes, because our boxes, not nature's boxes. So in a metallic bond, you typically still get a lattice structure. Different metals are more latticey than others. Others are a bit more amorphous. And the whole crystalline structure of metals is its own field that is well buried into metallurgy that I'm not going to get into. Now, in this case, I'm not putting the air quotes on the bond. Electrons are shared. So metal atoms will start sharing some of their electrons with each other. Not all of them will share electrons, but some of them will have electrons out kind of in the pool. And that kind of shared set of electrons is what we call the electron sea. You can kind of think of a metallic bond as being kind of like an ionic bond, except for the fact that there's no anions. That's replaced by a sea of electrons. So you have a bunch of positively charged nucleuses surrounded by a bunch of electrons, and this does allow them to slip and slide at least to some degree, which is why metals are malleable and ductile. And all of those electrons give really interesting electric properties, which is why metals are shiny. And of course, electricity is moving charge. You've got a literal sea of electrons. Hey, rivers flow, electrons can flow, and thus metals typically conduct electricity very, very well. Obviously, there is more to the story than what I'm describing. If you zoom out a bit, look at the crystal structure, things do change here. But this is kind of the core. Okay, so that's kind of your three major ways of looking at how atoms can arrange themselves. Typically speaking, if you've got nonmetals, those are probably going to do covalent. If you've got nonmetal and metal, that's going to typically be ionic. And if you've got metals and metals, then that's typically going to be a metallic bond. So with that said, have a wonderful day.